Okay, so we have these quiz problems. I roll the ball down a ramp. I estimate it's about 2.3 seconds. But give or take a couple of thousands. Okay. And I adjusted the slope, so it would take about 2.3. Okay, ball down the ramp. That just you watch one time, estimated delta t and delta x. I commented, I don't care if you think delta x is 48 miles, you can still solve the problem. Okay. But plus they make pretty good realistic estimates in the right general ballpark. Somebody, I think maybe even knew how long the thing was. So that's not one person's estimate. Had it right. But that's not important. It's what you do with the information, right? So we're wanting to find V naught and VF. And we, make sure everybody understood that was initial and final velocity and average acceleration, which is going to rely on you knowing what an acceleration is. Okay. And you certainly should by now. But if not, well, that's just something you got to fix. Okay. And I'll clarify it with that. Then I want you to estimate the velocity of the penny. Now, just to describe it, the beam was going around pretty fast, and I suddenly stopped it, and there was a penny laying on the far end of the beam. And I ask you to watch and estimate the velocity of the penny. Okay. So either the magnitude and angle of the velocity, or the I and J components of velocity, or the X and Y components if you prefer. And then I wanted to estimate the angular position of the penny at the same instant relative to the axis of rotation and the position in terms of I and J. Okay, not sure how many of you got to that part. So what am I seeing when I look at some of these? I'm seeing somebody using an equation to find the average velocity. Okay, which is okay, as long as you understand what the equation means, because you really want to understand what an equation means when you use it. Now you won't necessarily understand it. Some of the equations are a little hard to interpret. Meanings get harder and harder to interpret. But right now the meanings are pretty straightforward. So if you're using an equation, make sure you understand. But I'd say the average velocity is the average rate of change of position with respect to time. Just like the average angular velocity of the beam that we observe is the change in angular position divided by the change in time, right? Now that's instantaneous, it's not moving at a constant velocity, but you've dealt with that. You've got all kinds of data about how that changes, okay? And you can do calculations that I asked for, but I don't think I've seen yet from anybody. So I'm going to address that. Something. Either you didn't read carefully or the idea went over your head. But it's just the calculations of average velocity between observations. Okay. Yeah, I think we did that in class. I think they do little graphs and you get a straight line to the graph. See how that agrees with the derivative of the thing you got when you did the curve. Okay, well, anyhow, we need to get those things going, but I'll spell them out in the course of something really haven't seen. And I've seen a lot of good stuff. I've seen some well done write-ups, and I've seen some graphs, and I've seen people who actually did both of the curves that I asked for. Okay. And I kind of look back at what else I asked for that I was kind of looking for, but might not have asked for. Okay. And I'll comment on that later next time. Another thing is, it would have been good if I'd have gotten those in time, because then I'd have been able to go over them. But I'm going to do them all in the group. I don't want to do a piece again. So there's a reason for the deadlines. Anyhow, how do you get V naught and VF? Well, V naught is obvious, right? Started from rest. V naught would be 0. What about VF? Well, we'll talk about it. And then once you know what VF is, how do you get the average acceleration? You don't need a formula for any of that. None of it. But you can use the formula to get it. We want to make that connection so we both understand the idea and understand the formula and its use. Okay? And how to use formulas. So, what I'm saying. Give you hint, final velocity is not equal to the initial velocity, which is what I said, or not equal to the average velocity, which I see here, because it started from zero. How could the average velocity be equal to the final velocity? When you have, it doesn't reach the final velocity till the end. The average has to occur somewhere between the initial and the final velocity. Where should that be? Think about it for a second. Okay. And then there's a formula for the average acceleration based on the final velocity that I see. Yeah, you don't need the formula, but it's the right formula. It's the right answer. If you accept the wrong final velocity, which somebody said equal to the average velocity, right? But we'll fix that. That's easy. That's easy to compare. Okay. And what am I seeing here? I'm seeing somebody either knew made a really good estimate. The length of that thing is 24 inches. It's 2 feet. Standard length, so it's not that difficult. That's a correct. And estimated 2 seconds. I think it should estimate at least 2.2 or 2.4, since it was actually 2.3, as I know in the depths of my knowledge. Well, whatever. 2 seconds is a good estimate. So we've got a final velocity and an average velocity. I don't see any indication of why you think the average velocity was what it was. It has the wrong units, but I'm betting from everything else that I see that it was reasoned out correctly. But if I was grading this strictly, which I'm not, seeing if you're something to make an estimate, put things together. I wouldn't accept that answer because there's no support for it, just an assertion. And since it's equal numerically to the average velocity, matter of fact, it's identical to the average velocity. I don't know if you believe that the average acceleration is the final velocity, or you probably don't, but you understand. Understand what I'm saying? You got to support what you do. Even if you write out an equation that you don't really need, it's fine. If you got the right equation, I'm okay with it. But I want you to understand what they mean. Okay. Got something here about 9.8 meters per second squared. That's to drop something and it falls through. That thing is not falling through. Okay. But it's good that you know the 9.8 meters per second squared, because that's going to become real important very shortly. Incidentally, I generally do things with 10 meters per second squared and then do a 2% correction. Okay, just because it's easier, quicker, and we don't have to worry about multiplying by anything 10, which makes it easy. And then you can use 9.8 or 9.1, 9.81 meters per second squared. And that's not necessarily valid here because we're 2,000 feet out. We're further from the center of the earth than sea level. And that 9.81 and whatever decimals, they're meaningless because the density of the earth varies under the surface, different places. So you have a very uncertain acceleration of gravity. Okay. And we'd have to measure it electronically here. And we can actually do that and see how close we are. But we maybe should be. Okay, well, anyhow, that'll come later. Right now, we'll just assume 10 meters per second squared. Pretend Earth is a little denser than it is. Okay, then I see estimate of velocity. No units. And reasonable ratio of X to Y, but maybe in the wrong spot. Okay, so what am I seeing here? Somebody estimated 1 second at the time. It's a little quick, and that makes the calculation really easy, but got everything. Okay, Uh, okay. Uh, yeah, somebody assumed that final velocity was double the initial velocity. You didn't support that, but I don't expect you to necessarily know that you need to support it. Okay, and I'll show you how to support it without having to use formulas and then use formulas. And the velocity, estimated angular position of 290 degrees, which is a good estimate. It's actually about 320, but it's right. Yeah, whoever estimated that was sitting at a bad angle that we see it, something nothing wrong with that estimate. And as I said, we go from the estimate. If we do this in lab, we'll set it up so that we know darn well where it is. Yeah, with pretty good certainty. Then we do some things with the arc tangents and stuff like that. Looks pretty good. And that's kind of what I would hope. I see paper here where I think whoever wrote this one is a little uncertain about making estimates, reluctant to make them because you're not going to be 100% accurate. That's the mark of a good engineer. Okay. Yeah, it's a little stretch to ask you to make those estimates, but as I said, any estimate, even if you estimate something ridiculous, still gives you something to work with. Okay, well, let's go ahead and work through these quickly so that we can get on to connection with the equations and how to use them. Okay. And you will want to know that, but you want the concepts before you start throwing the equations, right? You don't have the concepts, and most people don't at this stage. At least you don't have them securely as you need them. Okay. And I want to start throwing formulas at the situation before there's a concept. Okay, well, so let's just say, okay. I'll use 2.5 seconds because it's easy to calculate. Okay, we can't do 2.3, but you know, sometimes we go catatonic for 3 or 4 minutes and waste class. So I don't want to do that. Okay, so we got delta T and delta X. Really, actually, it's actually 60 centimeters, which is 24 inches. Okay. Got about, yeah, actually we're close to 61 centimeters. I didn't start the thing right at the very back edge because it would have fallen off the wrong way. It could fall off the wrong way. Okay. So I was probably from the back edge, but anyhow, 60 centimeters. I use nice round numbers because they're easy to follow. Okay. So what can you conclude from this? Well, now, interpret these abbreviations. ROC is rate of change. WRT is with respect to. Okay. And this is what you know, some people are using the concept, rate equals distance times time or whatever. Okay. Yeah, that's fine, but this is a more sophisticated general definition that I want you to use. Okay. So it's equivalent for this problem. Okay. And if you use that, you probably got the right answer for the average velocity. If you use the units. What is this rate of change with respect to bring to mind? Well, somebody said last week, it sounds like a derivative, yeah. Now, if acceleration is constant, then velocity is linear because the rate is constant, rate of change is constant, so it's a straight line, so you don't have to worry about derivatives here. With the observations you made in our first lab, and y'all did a great job in that lab, getting the data and so forth. You get your curve fits and you're going to have to take some derivatives, right? You got what the velocity and angular velocity and angular acceleration functions are. And I thought I'd kind of ask for that, but I'm not sure. Okay. If not, if I did, I'll ask again, but make sure we get this. And if I didn't ask before, well, you know it's coming. It's derivative, easy derivative. Okay, there's your average rate of change of x with respect to time. And that equals change in x divided by the change in t. That's what a rate of change is. An average rate of change. An instantaneous rate of change is a dx dt, right? The derivative. And the average rate of change approaches the instantaneous rate of change if your delta t approaches zero. Unfortunately, we can't observe a delta t that approaches zero in a lab. So you gotta use averages and improvements and all that stuff. Okay, well, all that aside, this problem, the average rate of change is very simple, 60 centimeters over 2.5 seconds, which is 24 centimeters per second. Now, if you happen to write this down like this, it'll be a valid way to write it. But if you're not thinking of this as an instance of average rate of change, you're selling yourself short and you're failing to put an important concept on more firmer footing. And it's just a simple calculus concept, fundamental, maybe the fundamental. Actually have a fundamental concept for derivatives and a fundamental concept for intervals, and then you have a fundamental theorem that connects them. Okay, anyhow, you got your V bar. So that's a really easy calculation. I think almost everybody, I think maybe everybody got that. Even if you use the formula, you know, V minus V naught over T minus T naught. That's a valid formula, but does that formula really look like an average rate of change? It's closer to it, but that's what it comes down to. So I'll make a note. Okay, yeah, this could be. I'll use X out and X. X out and X naught, T out and T naught. Okay. But don't use this without thinking this. And don't use this without thinking this. That makes sense? Go back to the fundamental idea of rate of change, which people don't do, which is why, even though people have been through calculus, and I was the same way, although I was thinking about these things. It's easy to lose track of where all this comes from, and if you lose where it comes from, you're taking a chance. Okay. Okay. Okay, so there's our average velocity. Very straightforward, nothing to it. Now, this thing about final velocity, here's a picture. Now, length of this line here indicates the initial velocity, probably labeled further away from the axis. So here's V naught, here's Vf. And right here is V at any point. It's a straight line. Okay, well, we can just write this as a trapezoid. Here's V naught, here's VF, here's delta T. Where's the average velocity? Right here. I think I've drawn this picture before. It's at the midpoint of this segment because this is a straight line. The average of a linear function or linear quantity, well, linear function is the average of the starting and ending quantities. Okay. If it's not linear, it's not so. Reason this is because if I draw this rectangle here, which I think I've drawn, this little triangle here that's not included is equal in area to this triangle here that is included because of the linearity. So the area under this rectangle is the same as the area under this curve. The area under the rectangle is the average velocity times delta T. Okay? That's by the definition of average integrated. Okay, the area under the curve divided by the length of the interval, which in this case is delta T, is the average value of whatever it is that you're measuring in this direction. Okay, if the graph of that thing is a straight line. Okay, now if the graph is concave up, then the area under the curve would be less than the area under this. Well, actually, it would differ from the area under the rectangle to get from that color. Okay. Now that's kind of an important picture, and that would be a nice way to justify this. For example, you could write, okay, here's V naught. And sorry. I drew it this way just to show it's not always increasing, but in this case, the velocity is clearly increasing. So we have VF corresponding to the altitude of this triangle, delta T here. And VF minus V naught equals delta V. So here is delta V. Starting from 0, ending up with velocity, ending up at VF, right? So that delta V over delta T, which is your average acceleration, average rate of change of V with respect to T has to be then delta V over delta T. So your slope is rise over run. Which is the average acceleration. Makes sense? You need to ponder that a little bit. Okay. So there's your average acceleration, average rate of velocity with respect to time, because it's what average rate means. Okay. It's the average rate of change of something with respect to something In the case of acceleration, its velocity is expected time. But we put all this together. So from this picture, picture tells you that VF bar is VF over 2. Why? In this case, initial velocity is 0 and V is linear in T. This is not a formula you can apply in general. The formula you can apply in general is one of the 4 equations of uniformly accelerated motion that you've seen if you read through chapter 3, as I indicated you probably should do, for class today. If you haven't, you really need to read it. Okay. And I know everybody's pressed for time, it's obvious. Yeah, that's life for an engineering student. Putting all that together, your final velocity, since your initial velocity is 0 and the graph V versus T is linear, is going to be half your final velocity. Okay. Another way of saying it is it makes sense, average 0 and their final velocity, you get VF, right? VF plus V naught over 2. In this case, it's VF plus 0 over 2, which is VF over 2. You can see that by writing this out. It is legitimate for any uniform accelerated motion that you can find the average velocity by averaging the initial and the final. Okay. And it's also true as a result of this picture. There are 2 reasons why V bar is VF over 2. Okay. All right. So now, with all this justification and all these concepts that you really need to sort out in order to avoid the pitfall of grabbing the wrong equation in the wrong situation, and of failing to understand the subtleties of the problem. And of course, there are more subtleties than most people can understand at this point. Okay. So if you miss a little something, that's all, but try to get as much as you can. Okay. Again, using the, just gonna write it down. Okay. And I have written VF equals 2 times V bar, but it kind of follows V bar equals VF over 2, right? And you don't have to go to trouble of multiplying both sides of this equation by 2 to get that, but it doesn't hurt to do that once or twice. Just to kind of solidify the process. Okay, so VF is 48 centimeters per second. Average acceleration is delta V over delta T. delta V is 48 centimeters per second, since you're going from 0 to 48 centimeters per second. Start at 0 and up to 48 centimeters per second. The average acceleration is 48 centimeters per second change in velocity in 2.5 seconds. Right. 19.6 centimeters per second squared, which just turns out to be 1/50th the acceleration of gravity, doesn't it? 196 is twice 2.998, right? This is twice 9.8. This is in centimeters per second squared. That's in meters per second squared, right? This is 200ths. And again, might want to processing that. Have to understand when I said it. Okay. Totally understood when I said it. Lock it in. There it is. And then finally, we've assumed constant acceleration. Which is the same thing as saying that V versus T is linear. So we can write A equals 19.6 centimeters per second squared. Now, there's a lot of concepts involved in that analysis, but it really is very simple. If you're used to thinking about this, you say, well, I know how long and how far, so I can find the average velocity. I know I started from 0, so the final velocity has got to be twice as much as the average, because what do you average with 0 to get a quantity? Twice that quantity, right? Average twice something with 0, you get that something. And then knowing that, you can get your delta V, and there's your A bar. You can do this in this schematic diagram. It's going to be a little bit small, but it's important stuff all the time. Right? Okay, so what we can say is delta X and delta T give us V bar, right? Now, pay careful attention to this, because this is kind of a useful diagram. Okay. Now, there's another connection we can make. That is, if I know V bar and delta X, I can get delta T, right? So V bar and delta X go together to give us delta T. Or V bar and delta T go together to give us delta X, right? Then it can write it out. V bar equals delta X over delta T. So delta X equals V bar delta T. And delta T equals what? It's going to be delta X over V bar. And I know from experience, I was in this course many years ago, but I had calculus and linear algebra at the time, so you should be a little better than I was. If you look at this, it's a two-step process to get this, right? And it's conceptually a little confusing. You divide delta X by V bar, divide V bar by delta X. All right. Well, if you carry the units, it'll tell you if you did it wrong. Okay. Yeah, if you think a little bit about the quantities, it might even not make sense to you when you get the wrong answer. Okay. Might not make sense in terms of the situation. visualize the situation. Not always easy to do, but if it is something you can do, it's worth doing. Visualize the situation, make sure your answer makes sense. But you know, you got, what do you have to do to solve this for delta x? You gotta multiply both sides by delta t. And then you got to divide both sides by b bar, so you get this in 2 steps, right? Whereas this is just 1 step. Of course, this follows immediately from this, so if you've already got this, this is easy to get. Anyhow, meaning of that little triangle is any 2 of these gives you the third one. Make sense? Yeah, well, we can go even further than that then, of course. If we know b naught and b bar, what can we get? Well, we can get, yeah. B naught was 0, B bar was 24 centimeters per second. We know that if we average those two, I'm sorry, if we average this and this, we get this, right? So you kind of want to sort that out, then you can fill in steps on it. And then knowing P naught and P out, get delta V. Right? And of course, you know, V, delta V and VF, we can find V naught, we can look at delta V and V naught. We can find VF since complete triangle. And then finally, we know delta T and delta V get A. Of course, we know A and delta V, we get delta T. We know, well, delta V and delta T. Okay? So there's another little triangle in here. Each triangle has a set of simple relationships like this that you can use to help sort out the process. It's kind of almost like a flow diagram. You've had it in a program, okay? But it's not, but there's an analogy to it. Okay, it's kind of analogous. It gives you all your relationships. And you shouldn't try to memorize this. You should think through it and be able to construct your own. And it might not look exactly the way it does here, but the triangles all be the same. Okay. And the point is now, if I know any 2 things up here, I can find a third. So I can solve this problem just by taking 2 things and combining them. I took, it's down here now, but I took delta X and delta T to get V bar. Then I took V bar and V naught and I got VF. And it's not always twice as much, only if this is 0, right? But what would I average with this? But what would I average with this in order to get this? Even if this isn't 0, you can answer the question. It's just not a double, okay? And then I take 2 things that I've calculated. I take V naught and VF, and I get delta V. I didn't write that calculation down, but there it is. Okay, there's how I got that. So I took V naught and VF, I got delta V, and then I took delta V and delta T, and I got acceleration, and I never had to use an equation with more than 3 variables. Okay, if you're going to use equations, and these calculations should all be intuitive. You should think them through until they're second nature to you. It'll go a long ways. You can solve any linear motion problem for one object by reasoning like this, 2 things at a time, except for 2 possible situations. I'm going to tell you about those ones if we've got time, and we don't have a whole lot of time for understanding this. Okay. Very quickly, I'll talk about the vector stuff because there's some didn't have any apparent weakness with the vectors, but some people, most people did have some. not what I'd expect from somebody who's been through linear algebra and trigonometry. Okay, and calculus. So you want to make sure that you understand vectors. So, angular position, the penny. Well, here's our picture. Bar was rotating, and the bar was, well, you didn't see it, but I stopped the thing right about here. Okay, so that looks like about 30 degrees below the x-axis. So I'm going to say it was at 330 degrees. But if you thought it was 290, that's okay, especially if you're sitting at a bad angle. Okay, so here's the bar. It's rotating. Here's the penny. And here is the block that I put in the way. And the penny then went off in what direction? Well, okay. Penny position was 30 centimeters. In 330 degrees. Okay. So I could say the vector, the position vector, which is R, is thirty centimeters times the cosine of 330 degrees times your I vector plus 30 centimeters times the sine of 330 degrees times your J vector. Now that should be obvious if you understand vectors even at a rudimentary level. And it's fuzzy if it's not real clear to you. Work on it till you do, or email me a question or come by and ask me. I'll explain it to you a little further. Okay? I can write out an explanation if you email me a question. Okay? Share that explanation with everybody. Tell them who you were. You come by, I can show you. But I'm just going to refer you to basic trigonometry, which I assume you can review yourself. I'm not going to review basic trigonometry with you, but I'll try to clarify you on this. Can't spend class time doing that. Something you just got to know, especially after doing chapter 2. Okay, anyhow, there's your R vector. Now, if that's the case, what's the direction? Just without doing I and J vectors or anything, what's the direction of the penny's motion when it comes off here? How do you determine what the direction of the penny's motion would be at this instant? And I'm sure you could have given me that. Okay, so I got a good. Here's your velocity of the penny. Why is that the velocity of the penny? Well, I'm going to attempt. Because the penny is on this path. Okay. And the velocity is always tangent to the circle. These tangent to the circle. So here's the velocity of the penny. And of course, this is the radial line. The tangent is perpendicular to the radial line. Okay. So velocity is perpendicular to R. I didn't ask you to conclude that or anything, but I'm just taking off on what I hope you're trying to visualize, right? That you thought about the situation a little. This tells you a little bit more. Also, what's the condition for two straight lines being perpendicular? They have negative reciprocal slopes. Now, that should be second nature from pre-calculus, but people don't learn pre-calculus because it's usually taught to people who aren't going to ever come close to being engineers. And that's who they're focused on. And the engineers get short shrift. Now, most of you probably know it anyway, but some people might not. The whole negative reciprocal slope thing. Something you should be extremely familiar with, so you couldn't possibly forget it in 6 lifetimes. Okay? So from now on, make sure you know that well. If you don't already, and you might. Okay? This is a direction of one of these unit vectors. These are unit vectors. Don't know that? Go back to the very beginning of your linear algebra course. Hopefully you've got a text. One problem with most education now is you rent a text for a little while, then you don't have it anymore. Well, you can download online texts. Okay, plenty of information. Go back to unit vectors. Very beginning of linear algebra. And you should have reference to that. You need reference because there's stuff you're not going to remember that's important. Okay. Especially when you get into Hermitian matrices and all that stuff, as you will if you're in certain areas of engineering. Okay. Okay. Anyhow, there you have it. Now you estimated the magnitude and direction. There's no reason your two estimates here and here should be perpendicular, because you wouldn't have necessarily thought of that when you're just trying to visualize what's going on, right? But they would be perpendicular in reality. Now that's an important idea about vectors, and I'm not going to talk any more about it, but I really want to give you a better synopsis of the equation of motion. Okay. Now, equations of uniformly accelerated motion. That's a start. And from this, well, this is a basis for stuff that you're going to, that most students have a tremendous amount of trouble with around the end of October. Yeah, early November. Okay. I want to break the ice here so you get this idea down so you're not stumbling over it when you're trying to sort out a bigger idea. Okay. One of my strategies is started with this rotational motion. Okay. Now, I'm going to write the equation of motion a little bit differently than your textbook probably does. I don't remember how they write them, but I'll connect this with the way the book writes it. Okay? Because right now we're talking about just the relationships on some interval of time. You have some interval of the motion and you're trying to analyze it. That's as opposed to getting the function for the motion, in which case VF would be V and it'd be function V of T. And this would be a delta T, it would be a T, right? So I can actually write that. I'll write V of T instead of just V because your book just writes V and expect you to understand that that's a function of time and it has a graph. Okay? That's something you should be able to do, but I want to make it really explicit by putting the T in parentheses. Okay, no criticism of the book, it's a good set of equations, but it's easier to use it mindlessly if you don't understand this. And then when you get into an equation that involves most two things, and you got two graphs or a system of two simultaneous equations, you lose track of where the heck you are. I certainly did the first time I saw it. I resolved it a couple of days, but it took me a little time. Okay, it was too weird. I'd never seen anything like that. All right. Even though I'd seen plenty of simultaneous equations in three dimensions. Okay. Anyhow, that's one of your equations. Your other equation is another equation of delta x equals GF plus V naught over 2 times delta T. So that's something we just used, because that's average velocity times delta T. And then you have delta x equals V naught delta T plus 1/2 A times the square of delta T. This is how far you would move if your velocity didn't change. And this is how far you'd move if you started at 0 with this acceleration for this time. Now it's worth come back and maybe take the notes on, but I'll say it again later. Okay, then you have this. Now notice a couple of things. There are only five parameters in the system of equations. Okay. Any set of three of these parameters appears in at least one equation. Okay. And equation consists of exactly four of the parameters. I'm writing more than I intended to. Maybe a little hard to read. If you know the values of three of the parameters, you can find the value of a fourth using one of the equations. Just find an equation that has those three and solve for the fourth one. And once you have the fourth, you got all kinds of choices for equation to find the fifth. Sometimes you got two choices. of which equation to use for the three. Sometimes there's only one choice. Okay? So if I number these equations, I'm going to number them like this. This is number one, this is number two, this is number three, and this is number four. I wrote them in a different order. But remember, this equation came just by integrating constant acceleration one time. And if you don't remember how that was done, well, I'm going to have a test for too much longer. You're going to need to tell me. I need to show me. And this one came from a second. This is just a interval distance. Okay. And you should understand why, but fundamental theorem of algebra is finding derivatives of things that are of one of which is a derivative of the other. Okay. For the situation you have here. You know delta T, delta X, and V naught. Well, you don't need the equations if you understand anything I said earlier. I understand most of what I said. Because again, delta T and delta X give you average velocity. So in the initial velocity, you can figure out the final. Then you can figure out the change in velocity, and then you can figure out the average acceleration. So you got all five parameters. The ones you're missing, you're missing VF and A. Now, what equation contains delta T, delta X, and V naught? Does this one contain delta T? Yeah. Does it contain delta X? No, can't use it. Okay. What about this? Does it contain delta T? Yeah. Does it contain delta X? Yeah. Does it contain V naught? Yeah. What's it missing? V naught, VF. So we solved this equation for VF and plug our information in. Now we know everything but A. So any equation that has A in it is going to give us the result without having to think about anything. Okay? And I don't recommend that you do this without thinking of how you could solve it just by pairing things up like we did. Okay? This equation is the easiest to solve for A. You don't want to have to deal with squaring T. You don't want to have to deal with squaring V naughts and VFs. Okay? But you could. You would get exactly the same thing for A, this equation, or this equation, or this equation. But pick the one that's easiest. There's a strategy. Now, it comes down to being able to read a problem or understand a situation you have your hands on in the lab and know that you have three of these. There are only five of them. You just learn to identify them. Okay? It's a simple mechanical process, but don't use it without thinking. I mean, use it without thinking, then go back and think, how could I solve this just by understanding what these quantities mean? And okay, there are 10 possible combinations of V naught, VF, 10 possible combinations of three of these. Okay? And only two of those combinations do you need to actually use the equations. Okay? I'll talk about that next time. But in 8 out of the 10 possible cases, you can figure it out without using any equation if you know that average velocity is rate of change of position, average rate of change of position with respect to time, and average acceleration is average rate of change of velocity with respect to time. That's all you need. And reasoning. So I recommend that you reason as much as possible. At least you think about what you might be able to do. Don't just blindly use the equation and accept the result. Except if it's one of those cases where there ain't no way. Okay? And it's very quickly, there ain't no way cases are when you know PMOD. You know, either of these combinations, you're stuck. Okay? The only equations you can use are equations that are derived from these two really basic equations. Okay? And incidentally, this equation is obtained from these two by solving simultaneously and eliminating A. You solve this one for A, plug into this, and this equation comes right out. We'll talk about it next time. Okay? And then you take these two and eliminate T, and you get this one. So there are really only two equations. And then you eliminate one variable from those two equations, you get this, and eliminate the other, you get this. Okay? And these two come directly from integration. Useful to know that.